This is video 4A for the Year 11 Mathematical Methods course. In this video, we're going to cover the theory behind polynomials, under the topic of polynomials. Specifically, we are going to explore the general form of a polynomial, general polynomial terminology, key types of polynomials, the product of polynomials, polynomial equality, and then we're going to cover some example questions. Now, the topic of polynomials in this course is going to be quite an interesting one because, as a matter of fact, we've already been working with a few different types of polynomials in the past over the last few years. Our job in this course is going to be taking what we've already learnt and expanding it to quite a significant degree. Now, I very much see this topic of being very reminiscent to the quadratics topic because we're going to be covering quite a few similar aspects of what we've already covered with quadratics so far. Whether it be stuff like finding the x-intercepts and the roots of particular quadratics and graphing quadratics from equations and then finding equations from graphs and so on, a lot of the techniques and stuff that we've already learnt from the quadratics chapter will essentially be expanded upon in this polynomials chapter as well. So if you found all that stuff there not too bad, then hopefully this stuff when it comes to polynomials shouldn't be too bad either. Now, that being said, I earlier mentioned that we've already had a look at a few different types of polynomials, namely quadratic functions, and linear functions. So both of these are very prime examples of polynomials. And when we actually get into this whole discussion of polynomials, we will see that there is an infinite number of different types of polynomials. So we're going to start off this chapter by just going through some very general terminology and aspects when it comes to polynomial functions. And the first thing that we're going to cover is the exact definition of what a polynomial is. So by the formal mathematical definition, a polynomial is a function of the following format. Now, this definition here is a very important one because as we'll go through throughout the rest of this video, this mathematical definition here pretty much tells us everything that we need to know about polynomials. Now, with that being said though, I'm fully aware of the fact that right now this looks like a very terrifying thing to start off this entire chapter with. But do be rest assured knowing that despite how terrifying this currently looks, once we actually break it down into its individual pieces and we go through each of those pieces, you'll see that it's actually not too bad, and realistically it's actually quite easy to follow. So let's break this down into its individual pieces. So the first part that we're going to discuss is the x. In this particular case, we're going to say that x is the variable. So we've of course seen this time and time again, much like if we've got a linear function of y equals mx plus c, or if we've got a quadratic in the format of y equals ax squared plus bx plus c, we know that x is the thing that we can essentially assign a particular value. So whether it be 1, 2, -5, 0, whatever, x is the variable and therefore we can assign x any value that we want to. And now the next thing that we're going to go over are all of these an take 1, an take 2, a2, a1, and a0 terms. Because as they currently appear, I can understand how it might be a little bit confusing. The really nice thing is though, is that each of these are essentially just notations for coefficients, or in other words, just numbers. So we say that a subscript n, or a subscript n take 1, all the way down to a subscript 0 are the coefficients of the x to the power of k terms. Now when I say x to the power of k, I just mean the fact that x to the power of k could be x to the power of 1, x to the power of 2, x to the power of 3, and so on. And again, just to put your mind at ease, remember that these parts here are just numbers. So they could be a positive number, they could be 0, they could be a negative number or whatever, but they are essentially just numbers. The only reason why we notate it like this is we say that this a to the power of 0 is the 0th coefficient. Then we say that a to the power of 1 is the first coefficient, a to the power of 2 is the second coefficient, and so on. So it's just a bit of fancy notation when it comes to this. Then, if we just want to get a little bit more specific when it comes to a few of these different coefficients, we're first of all going to have a look at the a0 coefficient. Because the key thing about this a0 coefficient is the fact that this is the only one without an x term next to it. So we call this the constant term. And the reason why we call it the constant term is because no matter what value x is going to take, the constant term does not change its value because it does not have an x component attached to it. And then the other important coefficient that we're going to talk about is a subscript n. Now we call this the leading coefficient. And the reasoning for this is because the a subscript n coefficient always appears next to the highest power of x. So we'll talk about this in just a second, but essentially when we're talking about polynomials, there is always going to be a term in which the x part has the highest power. And in this particular case, the x power of n will be the highest power of x. So we call the a subscript n coefficient the leading coefficient because if you order all the different terms from highest powers of x to lowest powers of x, then this will always be first because it's attached to the term with the highest x power. So once again, just to quickly summarize, the constant term is called the constant term because it doesn't change its value no matter what the value of x is. And we call the leading coefficient because it is the coefficient of the term with the highest x power. Now, just a quick, really important thing about this leading coefficient. The leading coefficient, unlike all the other coefficients, is the only one that cannot equal to 0. So all the other coefficients from a n-1, a n-2, all the way down to a1 and a0 can be whatever value you want to give them, whether it be positive, negative, or 0. However, the leading coefficient cannot be equal to 0. And then the final definition to cover is this n value. Now we call n the degree of the polynomial. And again, just linking this back to what we were talking about with the leading coefficient, we said that this leading term here, so an then x to the power of n, is the term with the highest x power. So essentially the degree of a polynomial is the highest power in which x is risen to in the polynomial that we have. And then what we say about the polynomial is that each of the subsequent terms have powers of x which are 1 minus from one another. So in other words, we start off with this x to the power of n out the front, then the next one will be x to the power of n minus 1, then n minus 2, and we continue this all the way down until we get x to the power of 1, and then finally until we're just left with a term all by itself with no x component. Now, the really, really important thing about these powers of x's is that they have to be integers. Specifically, they have to be non-negative integers. So in other words, the degree must be a non-negative integer. So for example, it could be 1, 2, 3, 4, 5, 10 million, 500,000. As long as it's a non-negative integer, then the degree can be whatever value it wants to be. So what this here means is that if you have a square root or a reciprocal component in the function that you have, it means that these are not going to be polynomials. Because if you recall, the square root of n we can write as x to the power of 1/2, and then 1 over x we can write as x to the power of -1. In both of these cases, the power of x are not positive integers, therefore these kinds of terms here can never be part of polynomials. Again, I just want to re-emphasize this. The powers of x in polynomials can only be non-negative integers. So no fractional powers of x and definitely no negative powers of x either. So these are all the different components of the polynomial family, I guess you could say. So again, we've got the variable x, we've got the different coefficients of each of the different terms, we've got the constant term, which has no x component next to it, we've got the leading coefficient, which is the coefficient of the highest power of x term, and then finally we've got the degree of the polynomial, or in other words, the highest power of x in the entire polynomial. And now that we've had a look at all these key components of polynomials, we're actually going to delve in a little bit more specifically with a few of the key types of polynomials that we're going to focus on over the course of this chapter. Now the first two are ones that we've definitely had a look at before, specifically linear functions and quadratic functions. Then the two that we're going to be introducing quite extensively throughout this chapter are going to be cubic functions and then quartic functions. The first thing we're going to look at is the general form for each of these polynomials. Then we're going to have a look at their degrees. Then we're going to quickly define the leading coefficients. And then finally, the constant terms. The general form of a linear function is ax plus b. The key feature here is that the highest power of x is 1. But of course, whenever we write a power of 1, we don't necessarily bother with that, so I'm not going to bother with it here either. Then the general form of a quadratic is ax squared plus bx plus c. And again, the key feature of a quadratic being that its highest power of x is 2. Then for a cubic, it's ax cubed plus bx squared plus cx plus d. And then finally for a quartic, we have ax to the power of 4 plus bx cubed plus cx squared plus dx plus e. And now let's have a look at the degrees of each of these polynomials. So once again, for the linear, we realize that the highest power of x in this case is just going to be 1. So therefore, the degree of a linear polynomial is 1. Then with a quadratic, we can see that the highest power of x is 2. So we can therefore say that the degree of a quadratic polynomial is 2. With a cubic, it gets risen to 3. So we can say that the degree of a cubic polynomial is 3. And then for a quartic, we could see that increases to 4. Then, if we consider the leading coefficient, so for the linear polynomial, we can see that the coefficient of the x term with the highest power is this a, so we'll say that a is the leading coefficient. Then similarly, with the quadratic, the coefficient of the x squared term is a. For the cubic polynomial, we can see that the coefficient for the x cubed term is a. And then finally, for the quartic polynomial, we can see that the coefficient of the x to the power of 4 term is a. And now finally, the constant term. So again, these are the terms with no x component next to them. For the linear, it's just this b term. For the quadratic, it's the c. For the cubic, it's d. And then for the quartic, it is e. So a big part of this early chapter is going to be looking at different polynomials and understanding and identifying these three key things. The degrees, the leading coefficients, and then the constant terms as well. We will have a look at a few examples of this in just a second, but before we do that, I do need to go through one more really important thing, specifically when it comes to multiplying different polynomials together. Now, the reason why this section is going to be very important is because identifying the degree, leading coefficient, and constant terms of polynomials already in expanded form is actually a pretty easy process. So just as a quick example, let's say I gave you the polynomial of 3x to the power of 5 plus 4x cubed, take 2x, take 1. Then with this one here, we can clearly identify that the degree of a polynomial is 5 because this is the highest power of x. Therefore, the polynomial's leading coefficient must be 3 because this is the coefficient of the highest power of x term. And then finally, the constant term must be this -1 because it's the only term without any x component. So this process here is pretty straightforward once you understand the key definitions of these three different things. The problems then arise when we give you situations like this. Because the problem with this particular case is the fact that we've got two different polynomials being multiplied together. So in order to find the degree, leading coefficient, and constant term of this polynomial, we'll have to use the distribution law. In other words, we'll have to do this multiplication, this multiplication, this multiplication, then this one, then this one, then this one, and then this one, by this one, by this one. So you can have a total of 9 multiplications to do, in which you have to make sure you do each of them perfectly. Then you have to go about the process of collecting like terms, and only after you've done that, and you've written it in a format like this one up here, can you then easily identify the degree, the leading coefficient, and the constant term. That entire process there is a very, very tricky one to make sure you get right, especially when you're dealing with different polynomials which already have pretty high degrees. So now we're going to consider a way to make this process even easier. And the reason why I'm harping on so much about this right now is because throughout the rest of this chapter, we're going to be dealing with quite a few different situations where we have different polynomials being multiplied together, and we need to understand how to easily identify their degrees, leading coefficients, and constant terms. So trying to avoid this process here of expanding and then simplifying is going to be very, very beneficial for us. Now, in order to have a look at these rules, I'm going to present you with a very, very general idea. Let's say we've got the polynomial f of x, and we are going to define f of x as an x to the power of n plus a n take 1 x to the power of n take 1 plus yada 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 plus a2 x squared plus a1 x to the power of 1 plus a0. Then I'm also going to define a separate polynomial g of x. I'm going to define g of x as bk x to the power of k plus b k take 1 x to the power of k take 1 plus yada 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 plus b2 x squared plus b1 x to the power of 1 plus b0. So if we focus on f of x first, then we can see first of all that the degree of f of x is equal to n, because this is the highest power of x. Then the leading coefficient is an, because this is the coefficient attached to the x to the power of n term. And then finally, the constant term is this a0, because that's the only term with no x component. And then if we consider the polynomial g of x, then we can see that its degree is k, its leading coefficient is bk, and then finally its constant term is b0. And then what we're going to be concerned about is the polynomial that we're going to define as p of x, and we're saying that p of x is equal to f of x multiplied by g of x. So again, in this particular case, we're concerned about what happens when we multiply two different polynomials together. So then in a expanded way, what p of x is going to look like is this. And what we're concerned about now is how to easily identify the degree, the leading coefficient, and the constant term of p of x. Let's start off with the degree. Now, what we need to remember is that the degree is officially defined as the highest power of x within the polynomial. And what we defined previously is that n is the highest power of f of x, and that k is the highest power of g of x. So when we use the distribution law on these two polynomials, the multiplication that is going to result in the highest power of x is when we multiply this term by this term. Because what that multiplication equals to is an bk x to the power of n x to the power of k. And then if we want to combine these two terms here, we get an bk x to the power of n plus k. Because remember, when we multiply two different things with the same base but different powers, we just have to add the two powers together. So what this here tells us is that the highest power of this new polynomial will be n plus k. So the degree of p of x will be n plus k. Piggybacking off of this idea as well, we can then also identify the fact that the leading coefficient must be an bk, because this is going to be the coefficient of the highest power of x term. So we can say that the leading coefficient is going to be an bk. Now the last thing that we've got to identify is the constant term. And again, the constant term is the only term that has no x component attached to it. And if we have a look at all these different terms in these two different brackets, we can identify that the only multiplication that is going to result in a term that has no x component is when you multiply this term by this term. And that is purely because both of the terms originally have no x component. So when you multiply them together, it will still just be a number multiplied by a number. And of course, when we multiply a0 and b0, the result is just a0, b0. And so we can therefore say that the constant term of p of x will just be a0, b0. Now, this is all well and good, but we now need to understand how we can generalize these findings into a much more broader sense. Let's start off with the degree, because what we found about p of x is that the degree will be n plus k. However, what we can notice here is that we originally defined n as the degree of f of x, and k as the degree of g of x. So what this therefore tells us is that the degree of p of x is the sum of the degree of f of x and the degree of g of x. So in other words, if you've got two polynomials that are being multiplied together, the degree of the product will be the sum of the two individual degrees. Then furthermore, with the leading coefficient, we can recall that we defined an as the leading coefficient of f of x and bk as the leading coefficient of g of x. So therefore, the leading coefficient of p of x is the product of the two individual leading coefficients. And similarly with the constant term, because we recall that a0 and b0 are the two constant terms of the different polynomials. So therefore, the constant term of p of x is as well the product of the two individual constant terms. So now let's write these sets of rules in a much, much easier sense. So, if p of x is equal to f of x multiplied by g of x, then the degree of p of x is equal to the degree of f of x plus the degree of g of x. So that was this rule here. And then secondly, the leading coefficient of p of x is equal to the leading coefficient of f of x multiplied by the leading coefficient of g of x. So that was this rule here. And then third and finally, the constant term of p of x is equal to the constant term of f of x multiplied by the constant term of g of x. And that was this rule here. Now this set of rules here is going to be pivotal to simplifying a lot of these really, really difficult problems that we're going to be looking at throughout the rest of this chapter into very, very trivial and easy to solve problems. So I'm going to recommend that you get this down and that you look for different opportunities to apply these rules without having to go through the process of applying the distribution law to two different polynomials, then collecting alike terms, and then finding out the degree, leading coefficient, and constant term from there. Using these three rules is not only going to be easier, but it's going to be much more time efficient as well. Now, let's go through a few quick examples as to how we can identify the degree, leading coefficient, and constant term of different polynomials. The first one is 3x squared plus 5x take 7. So first things first, let's do the degree. So we can see here that the highest power of x throughout this entire polynomial is this 2. So therefore, we can say that the degree of a polynomial is 2. Furthermore, the leading coefficient, because we know that the degree of a polynomial is 2, then we know that the leading coefficient is 3 because this is the coefficient of the x to the power of 2 term. And finally, the constant term. The only term without an x component is this negative 7. So therefore, the constant term must be negative 7. Second example is 8x take x to the power of 4 plus 3x cubed plus 5x squared. So again, let's start off by focusing on the degree. So throughout this entire polynomial here, we can see that the highest power of x is this 4. So therefore, the degree of a polynomial must be 4. Then the leading coefficient. Because we know that 4 is the highest power of x, then we know that the leading coefficient must be this negative 1, since it is the coefficient of the x to the power of 4 term. So therefore, the leading coefficient is negative 1. And then finally, the constant term. In this polynomial, we can see that there is not a single term that does not have an x component. So therefore, the way that we can write this is 8x, take x to the power of 4 plus 3x cubed plus 5x squared plus 0. Because if we just add 0, that doesn't affect the overall polynomial. And so therefore, we're going to treat this here as our constant term, because again, that is the only term with no x component. Now, this next example is going to go into the idea of multiplying different polynomials together. Specifically, if we had 2x squared plus x take 1 multiplied by 3x plus 3. So, let's start off with the degree. So we of course recall that the degree of a multiplication of polynomials is the addition of the individual degrees. With this first polynomial, we can see that the highest power of x is 2. So we're going to put 2 plus, then we can see with the second polynomial, the highest power of x is 1. So we'll put this 1 here. So then the degree of the multiplication of these two polynomials will be 2 plus 1, which is equal to 3. Then the leading coefficient. We know that the leading coefficient of a multiplication of polynomials is the product of the two individual leading coefficients. So with the first polynomial, we can see that the leading coefficient is going to be this 2. And then with the second polynomial, we can see that the leading coefficient is going to be 3. So therefore, we can say that the leading coefficient of the entire thing will be 2 multiplied by 3, which is equal to 6. And then finally, the constant term. So we know that the constant term of the multiplication of two different polynomials will be the product of the two individual constant terms. The constant term of the first polynomial is -1, and then the constant term of the second polynomial is 3. So therefore, we can say that the constant term of the entire thing will be -1 by 3, which is equal to -3. And then final example we're going to go through here is x squared plus 10x cubed take 2x plus 3 multiplied by 3x to the power of 4 take 4x to the power of 3 plus 3x squared take x take 5. So starting off with the degree, we of course recall that the degree of a multiplication of different polynomials is equal to the sum of the individual degrees. With this first polynomial, we can see that the highest power of x is 3. And then with the second polynomial, we can see that the highest power of x is 4. So therefore, the degree of the entire thing will be 3 plus 4, which is equal to 7. Then the leading coefficient, we know is going to be equal to the product of the two individual leading coefficients. The leading coefficient of this first polynomial will be this 10, and then the leading coefficient of the second polynomial will be this 3. So therefore, we can say that the leading coefficient of the entire thing will be equal to 10 multiplied by 3, which is equal to 30. And then last but not least, we know that the constant term is going to be equal to the product of the two individual constant terms. The constant term of this first polynomial is this 3, and then the constant term of the second polynomial is this -5. So therefore, the constant term of the entire thing will be equal to 3 by -5, which is equal to -15. So these are just a few different examples as to how we can find the degree, leading coefficient, and constant term of different polynomials. Whilst it doesn't seem very difficult right now, we've got to keep in mind that these different parts of the polynomial essentially form the foundation of the rest of this chapter. So make sure you practice this quite extensively and make sure you understand the key differences of the degree, leading coefficient, and constant term, but more importantly, how to find them in a variety of different situations. Now, before we finish up with this little subchapter, there is one more really important aspect of polynomials that we need to quickly go through. And this is something called polynomial equality. Now, the idea of polynomial equality is a very simple one, and yet a very important and crucial one that we're going to be using throughout the rest of this chapter. Essentially, polynomial equality tells us that if we have two polynomials that are equal to one another, then all the corresponding coefficients are also equal. Now, to go through what this exactly means, I'm going to set up an equation where two different polynomials are equal to one another. So the first polynomial we'll just define as a n x to the power of n plus a n take 1 x to the power of n take 1 and so on. And we're going to say that this is equal to another polynomial, which we'll define as bn x to the power of n plus b n take 1, x power of n take 1, and so on. And because we're saying that these two polynomials are equal, then polynomial equality tells us that all the corresponding coefficients are equal. In other words, the coefficient of x to the power of n for this polynomial will be equal to the coefficient of x to the power of n for this polynomial. And then the coefficient of x to the power of n take 1 on this polynomial will be equal to the coefficient of x to the power of n minus 1 for this polynomial. And then continuing this along, we know that the coefficient of x squared for this polynomial will be equal to the coefficient of x squared for this polynomial, then x power of 1, x power of 1, and then even the constant terms as well. So if we now want to write these as a set of equations, we can say that these two coefficients are going to be equal. So in other words, an is equal to bn. Then we can say that this coefficient and this coefficient are equal. So a n take 1 is equal to b n take 1. And then I'm sure you can see the pattern where we're going from here. a2 is equal to b2, a1 is equal to b1, and then a0 is equal to b0. So if we really want to put this in simple terms, it means that if two different polynomials are equal to one another, then polynomial equality tells us that the terms with the same power of x also have the same coefficients. But then if we even want to expand a little bit further on this idea, we can also say then that the leading coefficients are equal and the constant terms are equal. And realistically, these two make a lot of sense. With the leading coefficient part, if we have two polynomials that are equal, then they must both have the same degree. So therefore, the coefficient of the term with the highest power of x on this side of the equation must be equal to the coefficient of the term with the highest power of x on this side of the equation as well. Or in other words, the leading coefficients must be equal. And then furthermore, we know that the coefficient of the term with no x component on this side of the equation must be equal to the coefficient of the term with no x component on the other side of the equation as well. Or in other words, the constant terms must also be equal. Now, the reason why these two parts here are very important is because when we're going through a lot of these different types of questions, often a lot of expansion and collection of like terms is going to be involved. However, if you can make your life as easy as possible by implementing these very straightforward rules when it comes to the leading coefficient of the constant term, and just as a quick heads up, you're going to be using these two rules in conjunction with these rules up here quite a bit when we're talking about the degree, leading coefficient, and constant term of two different polynomials being multiplied together. Using these rules in tandem with one another is going to make this whole process of finding out different coefficients significantly easier to avoid the use of any excessive expansion and collection of like terms. Now, with that being said, let's go through a few different examples as to where we can use polynomial equality. So for this first example, we're going to have the following equation. X cubed plus 4x squared take 7x plus 3 is equal to a plus 1 x cubed plus 4x squared plus 2bx plus c take 5. And our job here is to find out the values of a, b, and c. So polynomial equality tells us that the coefficients of corresponding terms are going to be equal. In other words, the coefficients of the x to the power of 3 terms will be equal, the coefficients of the x to the power of 2 terms are going to be equal, the coefficients of the x terms are going to be equal, and finally, the constant terms are also going to be equal. So let's start off by writing a few equations connecting each of these different sets of coefficients. So first of all, the coefficients of the x cubed terms, we therefore know that 1 will be equal to a plus 1. Then with the x squared coefficients, we know that 4 will be equal to 4, which of course is all good. Then with the x terms, we know that negative 7 will be equal to 2b. And then finally, with the constant terms, we know that 3 will be equal to c minus 5. And so now we can solve each of these equations to find out the values of a, b, and c. So first things first, if 1 is equal to a plus 1, we know that a must be equal to 0. Then if negative 7 is equal to 2b, then b will be equal to negative 7 over 2. And then finally, if 3 is equal to c take 5, then c is equal to 8. The second example that we're going to look at is this one here. 2x squared take 3x take 2 is equal to x take 2 multiplied by ax plus b. And in this particular case, we're being asked to find the values of a and b. Now for this one here, we're going to avoid the immediate use of expansion and then collection of like terms, and instead opt for using the leading coefficients and the constant terms. Because on the left-hand side, we can see that the leading coefficient is 2, and then if we apply what we learnt before about the leading coefficients of the product of two different polynomials, we can therefore say that the leading coefficient of the right-hand side will be equal to 1 multiplied by a, which of course is just a. And then if we move on to the constant terms, on the left-hand side we can see that the constant term is negative 2, and then for the right-hand side we know that the constant term will be equal to the product of the two individual constant terms. So we can say that the constant term for the right-hand side will be negative 2 by b, which is equal to negative 2b. So first things first, let's equate the leading coefficients. We can therefore say that 2 is equal to a, so that one's all good there. And then with the constant terms, we can say that negative 2 is equal to negative 2b, or in other words, b is equal to 1. And now third and final example, we're going to set up the following equation of 3x cubed plus 4x squared plus 6x take 13 is equal to x take 1 multiplied by ax squared plus bx plus c, and we need to find out the values of a, b, and c. So again, similar to the previous example, before jumping into any excessive expansion and then collection of like terms, we're going to start off by using the leading coefficients and the constant terms. So on the left-hand side of the equation, we can see that the leading coefficient is 3. And then on the right-hand side, the leading coefficients of both these parts are 1 and a. So therefore, the leading coefficient of the right-hand side will be 1 multiplied by a, which is just a. And now if we move on to the constant terms, on the left-hand side, we can see that this term is equal to negative 13. Then on the right-hand side, the two constant terms are negative 1 and c. And then if we multiply these two together, we get that the constant term of the right-hand side is equal to negative c. So now if we equate these leading coefficients in constant terms, we get that 3 is equal to a, so that one there is all good. And we also get that negative 13 is equal to negative c, or in other words, c is equal to positive 13. So now we can substitute in these values of a and c into the right-hand side of our polynomial equation. In which case we then get 3x cubed plus 4x squared plus 6x take 13 is equal to x take 1 multiplied by 3x squared plus bx plus 13. And now because this b value is neither the leading coefficient nor the constant term, this is the part where we now need to do some expansion and simplification. So if we expand out the right hand side, this is what we get. 3x cubed plus bx squared plus 13x take 3x squared take bx take 13. And then if we go about collecting like terms, we get 3x cubed plus b take 3 x squared plus 13 take b x take 13. Now, a really good step that you can implement at this particular point here is confirming that your leading coefficient and your constant terms are indeed the same. So for the left-hand side, we've got a leading coefficient of 3, which matches the leading coefficient of the right-hand side. And then the constant term on the left-hand side is negative 13, which matches the constant term of negative 13 on the right-hand side. So both of these are good to go so far. And so now we need to try and figure out what this b value is. We've got two different ways of doing this, and we're going to go through both of them just to confirm that we do indeed have the correct answer. The first thing that we can do is equate the coefficients of the x squared terms. So we've got this 4 is equal to b take 3. And then the second one is we can equate the coefficients of the x terms. On the left-hand side, we've got 6, and then on the right-hand side, we've got this 13 take b. And if we solve both of these, we get b is equal to 7, and similarly, we get b is equal to 7. Now, when you're doing these types of questions in practice, it's not necessary to go about solving for both of these different equations. However, if you want to be 100% certain that you've done the right thing, then this is a very, very good way of doing that. So then if we just want to quickly summarize our answer, we can say that a is equal to 3, b is equal to 7, and then c is equal to 13. Alrighty, let's wrap up what we've learned today. So in this video, we delved back into the world of polynomials. We defined a polynomial as a function that takes the following form. P of x equals a of n multiplied by x to the power of n plus a of n minus 1 times x to the power of n minus 1 plus yada 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 plus a of 2 by x squared plus a of 1 by x to the power of 1 plus a of 0, where x is the variable, a of n minus 1, a of n minus 2, and so on are the coefficients of the x to the power of k terms, where k is equal to n minus 1, n minus 2, and so on. A of 0 is the constant term, or in other words, the only term with no x component. A of n is the leading coefficient, or in other words, the coefficient of the term with the highest power of x. And then n is the polynomial degree, or in other words, the highest power of x, which must be a non-negative integer. The four key types of polynomials we have are linear, quadratic, cubic, and quartic polynomials. Their key features are summarized in this table. For p of x equals f of x multiplied by g of x, where f of x is a polynomial of degree n, with leading coefficient a of n and constant term a of 0, and g of x is a polynomial of degree k, with a leading coefficient of b of k and a constant term of b of 0, then p of x has degree of n plus k, leading coefficient of a of n times b of k, and constant term of a of 0 times b of 0. Then we looked into polynomial equality, which tells us that if two polynomials are equal, then all corresponding coefficients are equal. That is, terms with the exact same power of x have the exact same coefficients. Finally, we applied these key features of polynomials, as well as polynomial equality, to solve some exam-style questions. And that's it for now. See you in the next video.